transformations. And we may not get to all of these examples. I'm going to try my best, but I know Wednesdays are a little shorter as well. And there's just more explaining with these transformations. So you want to be able to describe a transformation of a function. A transformation is going to be where you're shifting a graph, and that could happen right or left or up or down. It could be a reflection of a graph, so where you're flipping it. It could be a dilation of a graph, which is where you're either stretching it or compressing it. So those are the transformations we'll talk about. Before we get to the transformations, I just want to talk about parent functions. So it says at the top, graphs are described as being part of a family. So a family of graphs is a group of graphs that display one or more similar characteristics. So for example, all parabolas would be a family of functions because their graphs are all parabolas. And then within a family, you know that there's a parent or somebody representing the parent or the parent figure in a family. So graphs, we have a parent graph. It's the graph of the parent function. It is the simplest of the graphs in a family. So this is the graph that's transformed to create all of the other members in a family. So just having that analogy with what you know to be a family outside of graphing. So these are 4 types of parent functions we're talking about. Really, we're focusing on the last 3. So one type of family we're talking about is linear, and that's kind of broken into 2. So we have constant functions, which are all horizontal lines. So the general equation of a constant function is f of x equals a. And remember, f of x is just y. So y equals a, where a is any number. It does give the domain and the range. Domain would be all real numbers. Range consists of a single real number a, because that horizontal line is only at one y value. But that would be the family of constant functions. So they are linear, but specifically they're all linear with a slope of 0. So then we also have the identity function, which also is linear. This is mainly what we're going to focus on for those functions that are linear. And the identity function is the function f of x equals x, or y equals x. It does pass through all points with coordinates a. So on that line, all points have, or at every point, the x and the y coordinates are equal. It's the parent function of most linear functions. And again, it says most because horizontal lines are also linear functions, but they're in that separate family. Domain and range for all linear functions are all real numbers. Then we have absolute value functions, which we talked about yesterday. So these are all functions with a graph that makes a V. The parent function of an absolute value function is f of x equals the absolute value of x. The domain, as we talked about yesterday, is all real numbers. The range is the set of real numbers greater than or equal to 0. So the parent function has that vertex at 0, 0 at the origin. And then that range, obviously, we talked about changes if the graph is shifted around. And then we have quadratic functions. So we do spend all of Chapter 4 really looking at quadratic functions, but they're just previewed here with transformations. So the parent function of a quadratic function is f of x equals x squared. Domain is all real numbers, and the range, just like absolute value, is all real numbers greater than or equal to 0 because parabolas also have a vertex, and that vertex for the parent graph is at 0, 0. So I'm going to include on here, before we really start talking about transformations, formulas for the linear, absolute value, and quadratic functions that I'm going to have you use while we describe transformations. Linear functions, I know we're familiar with y equals mx plus b, but when we describe transformations, we describe them in terms of the a values, h values, and k values in an equation. So I'm going to write a formula for a linear function using a, h, and k, so it will look different than y equals mx plus b. So it's y equals a times the quantity in parentheses x minus h, and then plus k on the outside. So it's still linear, Here the A would represent the slope. The K is not the y-intercept. It kind of depends also what the H is. But like I said, when we actually talk about the transformations and talk about A, H, and K, that's why I'm giving you this formula and not just y equals mx plus b. So then there's similar looking formulas for absolute value and quadratics. For absolute value, it'll basically look the same, but instead of parentheses, we have absolute value bars. So y equals A times in absolute value bars, x minus h, and then plus k on the outside. So you need absolute value bars for an absolute value function. And then quadratics will also look similar. Y equals A times the quantity in parentheses, x minus h. However, quadratics, what makes a function quadratic is that power of 2. So it's the quantity x minus h squared, and then plus k. You may remember from Algebra 1, this is what's called a vertex form for a parabola. If you don't remember that, it's fine. But if it kind of looks familiar, that might be why. So one goal is being able to recognize when you see an equation, is it linear, absolute value, or quadratic? So you're looking to see, does it have absolute value bars, does it have a power of 2? But then also describing the transformations. So just take a note of where the A, H, and K values are. A for all three forms is a number that's multiplied in front of the quantity that has x. H is always inside with the x. So it's either inside parentheses or inside absolute value bars, and it's always added or subtracted from x. And then K is always outside of the function, outside away from the x, being added or subtracted. So I've already described here the types of transformations, the shifting or the reflecting or the stretching and compressing. We're first going to talk about translations. That's in this first box here. A translation moves a figure or a graph either up, down, left, or right. So this is going to be looking at the h and the k values. So when a constant k is added to or subtracted from a parent function, the result, so they write this in function notation, all this is showing is the plus or minus k is outside of the function away from the x. So just like in our formulas, it's added or subtracted from the end. This is a translation of the graph either up or down. So k is going to shift a graph up or down. If k is greater than 0, so it's positive, it shifts it up. And if k is less than 0, which is negative, it'll shift it down. And then h, so when a constant h is added to or subtracted from x before evaluating a parent function, the result, so again it gives this function notation. Again, just to notice, the plus or minus h is inside with the x, so I talked about that being inside parentheses or inside absolute value bars. This is a translation left or right. So if h is negative, less than 0, it's going to shift it to the left, and if h is positive, so greater than 0, it shifts it to the right. So if we look at, and you might be flipping back and forth a little bit, but if we look at examples 1 and 2, these are both translations. We are going to describe the translation and graph the function. And the graph is just going to be a sketch. So I'm not looking for your graphs today to be made using tables or anything like that. They don't have to be super precise. We're just sketching using the transformations. So looking at example 1, we have y equals the absolute value of x plus 2. Bless you. The plus 2 is what is transforming the graph. So we're starting with the absolute value of x and then transforming it by adding 2 to the end. If you take a look at your formulas on the front for absolute value, is the plus 2 an a value, an h value, or a k value? K, it's added at the end. So here, k would be positive 2. K shifts the graph either up or down. So because this is positive 2, it's shifting it up. So here's how I would like you to describe them. I'm going to say this is a translation of, name the parent graph, so we're translating y equals the absolute value of x in this case. And then how are we translating it? We're translating it up 2 units. So it's a translation of y equals the absolute value of x up 2 units. And then here's all I'm looking for you to do when you sketch the graph. I'm going to sketch the parent graph. So the parent graph, y equals absolute value of x, I know is a v, and the vertex is at the origin. That's about as precise as you need to get with it. You don't need to make a table to plot specific points. You're just kind of sketching it on that grid. So that would be the parent graph. And I'm going to use a different color. It's up to you how you want to do it. But all I'm doing then to this graph is moving that vertex up 2. So now it's going to be at 0, 2 on the y-axis. The shape of the graph stays the exact same, just the vertex moved. And that would be a sketch of the new graph, shifted up 2. So using transformations, this is kind of a way to get quick sketches of graphs versus really precise points plotted. Questions on number 1? Okay, number 2, we have y equals the quantity x plus 1 squared. So first of all, we don't see absolute value bars, but is this a linear or a quadratic function? Quadratic, we have a power of 2, so it's going to be a parabola. The plus 1 that is inside of the parentheses is what is transforming this graph. Is that an a value, h value, or a k value? H. It's inside with the x. Now, the h value here is not positive 1. The h value is actually negative 1. And I'll explain why. In the formula, which I'll write up here, I know it's on the front, but just so you can see it, y equals a times the quantity x minus h squared plus k. Notice in the formula, you're always subtracting the h value. So if I see plus 1 here, this is really the same as saying x minus negative 1. And h is the value, like I said, that you're subtracting. So if I'm adding 1, I'm really subtracting negative 1, which is why h is negative 1. So h, I guess an easy way to think of it, h is always the opposite sign of what it appears to be in the function. So if you see plus, h is really negative. If you see minus, h is really positive. And then since h is negative 1, h is going to shift the graph left or right. Because it's negative, it's going to the left. If it was positive, it would go to the right. So I would describe this by saying I have a translation of the parent graph, which is y equals x squared for a quadratic. And it's translated left 1 unit. Translation of y equals x squared left 1 unit. So then to sketch this, if I sketch the parent graph, it's just a parabola, vertex is at 0, 0. Again, doesn't have to be super specific with other points other than making sure your vertex would be at 0, 0. So now if it's shifted or translated left 1, the vertex just moves over to be at negative 1 on the x-axis, so at negative 1, 0. The shape of the graph, though, is staying the same, just the vertex moved. Okay, so I didn't include more examples of just translations, but there's an example of being translated up or down with a k value and then left or right with an h value. Are there questions on those? Okay, then the next type of transformation is a reflection, and there's, well, I'll explain here. The reflection is going to flip a figure over a line called the line of reflection. The lines we reflect over here are going to either be the x-axis or the y-axis. So depending on where the -1 is multiplied in this case, that tells you what axis to flip it over. So if a parent function is multiplied by -1, the result would look like this. So the negative is multiplied on the outside, not inside with the x. This is a reflection in the x-axis or over the x-axis. But if the variable is multiplied by -1, meaning inside the parentheses with the x or inside the absolute value bars with the x, if the x is negative, this is a reflection in the y-axis. So if you see a negative being multiplied, first of all, trigger reflection in your mind. And then you just have to determine where the negative is being multiplied, outside of the x or inside with the x. So if we look at 3 and 4, for number 3, y equals negative absolute value of x. So the negative is outside of the absolute value bars, not inside with the x. So this would be a reflection over the x-axis because it's outside. So to describe this, I would say it's a reflection of the parent graph, which is y equals absolute value of x, over the x-axis. And then to sketch this, so again, I'm going to sketch the parent graph, which is a V vertex at 0, 0, and it opens up. So now if you think of the x-axis as a mirror, because it's reflecting over the x-axis, the vertex is going to stay where it is, but now that absolute value graph will open down. So I know I'm using 2 different colors, but whether or not you're using 2 different colors, if you draw both the parent and the reflection, it's just going to look like you have a huge X on your paper for this one. All right, and then number 4, this is y equals negative x. So first of all, what type of function is this? Linear or quadratic? Is it going to be a line or a parabola? I heard something, I didn't hear exactly what it was. Linear or quadratic? How can you tell the difference between linear and quadratic? If it's squared, thank you. So if there's an exponent of 2, it's quadratic. There's no exponent of 2, so it's linear. So it's going to be a line. So the parent graph for this one, I'll just draw that right away, is a line. It's the line y equals x. So it goes through 0, 0. It has a slope of 1. A quick way to draw it is it goes through the bottom left and top right corners of your grid. So that's the parent graph. But now we have y equals negative x. So the question for this one is, would you say that negative is outside of the x or inside with the x? Well, first of all, there's no parentheses, right? So it kind of looks like it's outside. If I put parentheses around this, would you say I added parentheses, but did I change the function itself? If I just put parentheses around it, I'd say no. So this one for a line actually could be described either way. If you think of it as being outside, so no parentheses, it would be a reflection over the x-axis. If it's inside with the x, now it's a reflection over the y-axis. But either axis you reflect this line over, your graph will be the same. Because if I reflect over x, this piece reflects down here, this piece reflects up here. So it would look like this. If I reflect over the y, hopefully you can picture that it would just be going the other way. It would be going down instead of going up. So I can describe it either way. I can say this is a reflection of the parent graph, which is y equals x, over, and I'll say the x-axis or the y-axis. So this one could be either one. You wouldn't have to say both. I'm just saying both to show you that it could be either one. And then the actual transformed graph would be this line here. Either way you reflect it. Okay, any questions on the reflections? Okay, then dilations are the last transformation we're going to talk about. So a dilation shrinks or enlarges a figure proportionally. So this is going to be, for our purposes, this is going to be the A value in those formulas that I gave you on the front side, or the formulas I had you write down. So this would be the value that's multiplied in front of the quantity with x. So if the function is linear, the A value, as I had written on the front, is your slope. So it's changing the slope of the graph, either making it steeper or making it flatter. When a function is nonlinear, the function then would be described as being stretched or compressed vertically. So stretching it out is going to make it appear narrower. Compressing it would make it appear wider or flatter. So here it says coefficients greater than 1 cause the graph to be stretched vertically. So if your A value is greater than 1, it is stretched vertically. And then coefficients between 0 and 1 cause the graph to be compressed vertically. So that would mean your A value is between 0 and 1. So it would be a fraction that is smaller than 1, would be another way to say that. Fraction or a decimal. So a few examples here to look at. I'm actually just going to cross out number 8 for right now. That might be something I come back to maybe that first review day Friday to talk about. It was kind of an extra. I don't believe there's any on your practice that are like this one because it's a little bit different. But 5, 6, and 7, notice the value that's multiplied in front of the x or outside of the x. That is your A value. So we're going to describe these transformations. So for 5, our A value is 4. So that is a value that is bigger than 1, meaning it's going to stretch the graph vertically. Now this is y equals 4x. There's no x squared, so it's linear. So I can describe the transformation by saying this is a dilation of the parent graph y equals x. And then I want to describe what the dilation is, and that's either a vertical stretch or compression. So I can say dilation of y equals x stretched vertically. Again, it's stretched because the A value is bigger than 1. So how that's going to look on a graph, and as I talked about with linear functions, it's making that line steeper. So here's the parent graph again, a quick sketch. So if I stretched out this line, which is just making it steeper, it's going to go through the same y-intercept, but it's just rising faster. It has that steeper slope. So that would be the new graph. Okay, 6 is similar because that A value is 2, which is also greater than 1. But here it's y equals 2x squared, so it's a quadratic because of the power of 2, so it's a parabola. So since our A value is bigger than 1, I am still going to say this is a dilation of this parent graph is y equals x squared, and it's still stretched vertically. But here you can see what this looks like for a parabola. So I'm going to just quick sketch the parent function with a vertex of 0, 0. The vertex is going to stay where it is, but if I'm stretching it vertically, just think if I took where these arrows are and just pulled them up, it's making it narrower. So a vertical stretch graph would just be skinnier like this. And if it was compressed, it would make that parabola open wider. It would kind of shrink it down. So the last one, because I know Wednesdays are short here, but the last one, the y equals 1/2 absolute value of x. Just this one because that value is not greater than 1. So here the a value, because again it's outside of the absolute value, so it's a, is 1/2. That is a value that's between 0 and 1. It's not bigger than 1, so it's a vertical compression. So this is a dilation of y equals the absolute value of x. And now this is compressed vertically. So quickly what this looks like, again, if I draw the parent graph, the vertex again will stay where it is, but now I'm shrinking it down. It's going to make it open wider. And that would be true for parabola as well. So don't worry about 8. I don't believe there's any like that in the assignment. And then there might be a problem like number 9. I know we didn't get to it, where you have multiple transformations. Just pick out your A, H, and your K and describe what's happening.